Okay, so let's get started here. So we will continue our discussion on remote procedure call from last time. Today we will talk about remote method invocation, and I'm going to show you how RMIs are implemented in many different contexts: Java, Python, C, and so on. We will also hand out the first lablet today. The lablet is like a tutorial, really. Will just show you some sample code, you try it out so you get a sense of all of these topics, because the lab that's going to come out soon will require you to use either RPCs or RMIs to implement some distributed application. So this is just a way for you to get familiar with some of these concepts by actually playing with code. Okay? So we'll start with some RPC models. We'll talk about RMIs, which are really RPCs in the Java world. And then there was a couple of slides I didn't finish last time. I will cover that along with some other implementation examples in part 3 of the lecture. Okay? So that's the agenda for today. Let's start with some RPC models. And the first one I'm going to describe is what is called a lightweight RPC. Okay? So remember, what is a remote procedure call? It's the ability for an application process to invoke a method that resides in another process, potentially somewhere else on the network that's running on some other machine. Okay? So you invoke a function call or a method call. It just so happens that the code for this method is not in the process that's invoking the method. It's in some other process. Okay? So you have to communicate over the network to that process and actually execute the method, get back a response. Okay? All of that work is done by the RPC runtime, but that is what an RPC is. That's what we discussed last time. Okay? So today we'll talk about a lightweight RPC. So the lightweight RPC, think of it as a special case where both the client process and the server process are on the same machine. Okay? The general case is where the two processes that are communicating using RPCs, they reside on two different machines, okay, that are over a network. Okay? But in the special situation where the client and the server are on the same machine, you can optimize the RPC runtime system, and that optimized version or the special case version is referred to as a lightweight RPC. Okay? So what can we do to actually make this more efficient? So the RPC code is no different, okay? Because when as a programmer or a developer, you write the RPC code, you are simply invoking a method. Okay? You don't have any notion of where the process resides that's going to execute the method. So in this case, it just happens to reside on the same machine. So from a programming standpoint, there's no change. Okay? But from an implementation standpoint or the runtime standpoint, there is a change, because these two processes, the client and the server that are communicating using RPCs, they're on the same machine. Okay? So normally, when you invoke an RPC, okay, the stub code is going to generate a message, send it over a network. The protocol stack at the other end will process it and then hand it back to the server code to execute the method and so on. Okay? In this case, because the two processes are on the same machine, you can bypass the protocol processing. Okay? Instead, you can actually use a shared memory buffer to communicate between the client and the server. So rather than sending the message to the server saying, here is an RPC call, you can take the contents of that message and simply put it into a buffer and then signal the other process saying, here is a request that requires you to execute a procedure call. All the arguments are in the shared buffer. So rather than using TCP/IP messages to communicate between the client and the server process, we are going to use shared memory or shared buffers to communicate. If you remember last time I was talking about unstructured communication, where I said you could use shared memory to send messages back and forth. Message here is simply the fact that you put some data into a buffer and you ask the server process to execute it. Okay? So that's how we are going to optimize the performance. And as you can imagine, simply reading and writing from a buffer is going to be more efficient than using a socket-based communication, which requires you to establish the socket, construct a message, and send it over the protocol stack. You are essentially eliminating all of the protocol processing overhead. Is that clear? Okay. So there are some details of how all of that works, which I'm going to go through very briefly. There's a picture there, but the picture is not showing that there is actually a shared memory region. But what you need to really think about is there's a shared memory buffer that's not shown in this picture, that the client process will put the message, and then the server process will actually take the message and process it. Okay? But generally the way it's going to work is you will essentially push the argument onto a stack. You will trap to the kernel. The kernel will take the region of the stack where you push the arguments, that's your message that you're supposed to send, and make it available to the address space of the server. Okay? Normally the memory region of any process is not accessible to another process. Yes, because the memory region is private to a process. You cannot simply access the memory belonging to another process, because then you can overwrite it and cause problems. But in this case, because we want to explicitly share memory, we will instruct the OS to actually share that memory region. Then essentially the server process will take that contents from the stack, execute the method that is being invoked, put the return value, and return back to the client. Okay? So those are some of the details of how this works. But by and large, the bigger takeaway is you are not going to use protocol stack processing and messages. You are going to use shared memory to communicate between the client and the server. Yes, question.
What is trap?
Yeah, question is, what does trap mean in this context? So that's an OS term, right? So essentially, when you make a system call, okay, you create an interrupt to the OS. The OS is then going to execute that system call. Okay? The interrupt is referred to as a trap. Okay? So essentially, you go into a trap vector and then you execute the system call. So it's like a hardware interrupt, but in the context of a system call, it's called a trap. Okay. Yes. Any other questions? Okay. So that's one model, which is lightweight RPCs, but there are several others I'm going to discuss much more briefly, and I'll show you some figures that give you some sense of how these are different from one another. Okay? The standard RPC model is referred to as synchronous RPC. Okay? Synchronous means blocking. Okay? So when a client makes an RPC call, it's going to block or wait until the response comes back from the server. That's the definition of what we mean by synchronous RPC. Okay? So there are other models, as you can see. There's something called an asynchronous RPC, deferred synchronous RPC, one-way RPC, multicast RPCs. And the difference between all of them is how is the interaction between the client and the server changing based on what the client waits for, or whether it waits for anything at all. Okay? So we'll take them one at a time. So what happens in the asynchronous RPC is the client will make an RPC call. Okay? The call is now sent to the server, but the client will not wait for the reply to come back. Okay? It will simply wait for the RPC call to reach the server, and then it will continue execution. Okay? And at some later point, the reply is going to come back to the client, and then it can process the reply that came from the RPC call. Okay? So this is non-blocking. Okay? You're not blocking and waiting for the RPC to complete at the server, and you just simply continue execution. Okay? Deferred synchronous RPC essentially uses two RPCs, two asynchronous RPC, one in the forward direction, the other in the reverse direction. In this case, the reply is sent as RPC in the reverse direction. And I'll show you a picture that explains this. A one-way RPC is essentially even simpler than asynchronous RPC. The client makes an RPC call, and it simply continues execution. It doesn't wait for the call to even reach the other end, which at least the asynchronous RPC does. Okay? So that's called one-way RPC. Multicast RPC says you can make the same call to multiple processes. The RPC call goes to multiple server processes, which is useful when there are replication and you want to make the same request of multiple server replicas. Okay? So I think this is all best illustrated using some figures. Okay? So here is your synchronous RPC. Okay, I showed this last time. Okay, there's a client and a server. The client makes an RPC call and is going to wait all the way until the reply comes back from the server. The RPC call goes over the network, server executes it, generates a reply, response goes back. Okay? That's synchronous blocking RPC. Okay? Client is blocked until a response comes back. Okay? That's an asynchronous RPC. So what you will see is the client makes an RPC call, okay? And it waits for the server to do an accept on the socket, which means that the server actually has accepted the call. It's not processed it just simply received the socket connection to start processing it, and then it continues execution. Okay, so all of the other stuff is going to happen in parallel, because you will then, the server will receive the RPC request, process it, and the reply will go back to the client at a later time. Okay, this is non-blocking. Okay? You don't block for the RPC to execute and a reply to come back. Okay? Also called asynchronous. Okay, all right. So there are some more that we talked about. Okay, so here is one. Here is essentially the final step of the asynchronous RPC. You will see that there is a reply that went back at a later time through a callback. Okay. All right. So here is our deferred synchronous RPCs, where we use two asynchronous RPCs. One where you make the request to the server, and then you continue execution, and then the server executes the called procedure, and then the return value is sent as a RPC in the other direction, asynchronous RPC. Okay, so you will just send a request which includes the reply of the previous RPC. Okay, so you have two RPCs, one going in the forward path and the other coming in the reverse path. Both are asynchronous in this case. Okay, so instead of a callback, you will use a RPC in the reverse direction to send the reply. Okay, and this is our multicast RPC, where the client, there are two servers, S1 and S2. The client makes a single RPC request. It's sent to two processes. Both of them are going to execute that RPC call and send back a reply. Okay? And this one, as you see, is actually shown as a synchronous blocking multicast RPC. Multicast essentially means you're sending that to multiple recipients. Is that clear? Okay. So for most of what you're going to do in this course, you will use synchronous RPCs. Okay, that's the default model. Okay? But you should know that there are these other models that are useful in certain contexts. Okay? What those contexts are may not be clear as to why you would use something different from blocking. Okay, but as we look at other topics in this course, you will see there are different ways to write server processes, and some of them use asynchronous methods, and that's where you will use some of these other techniques. Okay, but for now, all you need to understand is what these methods mean, okay, or what these types of RPCs mean. Any questions on this? Okay, so we will change gears and talk about RMIs. Okay, so if you program in Java, okay, RMIs are essentially how you have clients and servers communicate using RPC-like ideas. Okay, RMI stands for remote method invocation. Okay, and the idea is very similar to what I talked about last time in the context of RPCs. Okay, so let's say you're writing a Java program. Typically, you will write some classes. Classes will have some methods. Okay, during execution of that program, you will essentially have objects that get instantiated. When you execute a class, you instantiate an object, and then you call methods on that object. Okay, the code for all of the classes are part of a single Java process. Typically, that's how a Java program is going to work. Right? Now, when you want to implement RPC-like ideas, okay, you will essentially still write your code as classes. Okay, and then when you execute the code, you will instantiate objects on these classes, except that in some cases, some objects will not reside in the process where you are invoking methods on that object. Okay, so you can say, let's say object1.foo, where object1 is an object and foo is a method you call on that object. Okay, so in this specific case, that object is going to reside in some other process. Okay, and it's going to expose a method that can be invoked over a network rather than some process invoking it locally. Okay, and so this is called a remote method invocation. So the method is remote and you're invoking it. Okay, so the objects are also remote in this case. Okay, so essentially you're using object-oriented ideas, but you are now using those concepts that you're already familiar with to implement RPC-like abstraction, but we'll call them RMIs in this case. Okay, or remote methods. Okay, so essentially the way you are going to do this is that object that you have written, which is remote, you will essentially write it in two pieces. You'll write an interface. Okay, in the interface of an object basically says these are the public methods of that objects, and these are the ones that can be accessed remotely and so on. And then there's an implementation of that object. The implementation will reside on the server. Okay? The interface will be available to the client, so it knows what are the methods the object is actually exposing, so you can invoke it over a network. Okay? So you'll have to separate the interface from the implementation, which you can do even when you don't use RMIs, but that's the way we are going to use it. So interface will reside on one machine, implementation will reside on another machine. Okay? So here's the picture of how RMI works. You will see that conceptually it looks very similar to the picture I showed you last time when I was talking about RPCs and the add method. Right? So there's a client machine, there's a server machine, there are these two processes. In this case, they're Java processes. So here is essentially a local object, okay? And it has some code and it's invoking a method on another object. Okay? It just so happens that this other object essentially is on the server machine. It's not local. Okay? So it's a remote object. And so that remote object here has some state shown in gray, and it is exposing some methods that can be invoked. Okay? In this case, the methods are remote, can be invoked remotely. Okay? And there is stub code on both the client machine and the server machine that's responsible for communicating between the client and the server. As a programmer or a Java programmer, you will not write any such code. You will simply call objects, not objects, methods on objects, and then the stub code is going to take care of sending a message over a network and so on. Okay? In the Java world, the stub code is referred to as a proxy on the client side. It's called a skeleton on the server side, but it's really stub code. It's auto-generated code, which the programmer does not write. Okay? So in this case, when the client is invoking a method, you're going to go to the proxy. The proxy will construct a message. The message will be sent over a network. It will arrive at the server stub code, which will then invoke the actual object and the method that was invoked on that object, execute it. The reply will go back in the other direction. Is that clear? Okay. So with that, let's look at some details of how all of this is going to work. As I said, the client stub is called the proxy in the Java world. The server stub is called the skeleton. Okay? All of the details that we talked about of how to make RPCs work also arise here. Okay? Specifically, we are not going to assume that the client machine and the server machine use the same hardware. Okay? They both run Java, so they will have a Java implementation. They will have a JVM and JDK and all of that, but you will not assume that they run on the same machine. Right? So one could be Windows, other could be Mac. Hardware may be different. One would be Little Indian architecture, the other could be Big Indian. All of those issues are still present in this case. Okay? So we still have to worry about when you send some data over from the client to the server, how do you deal with that, all of those differences? Okay? Now, in that case, we were using something called marshalling and demarshalling, which basically meant that you converted all of your data into an external data representation and then reconverted it back to native representation. That allowed you to overcome these hardware differences. Okay? The Java world, this is much simpler because Java supports something called serialization of objects, okay? Which essentially tries to write out an object in a hardware-independent format or any data structure in a hardware-independent format. So we can simply use serialize and deserialize operations for our RMI communication. You can essentially take all the arguments, serialize them, send them over, and deserialize them. And the serialize, deserialize automatically takes care of when you reconstruct the data structure or the data, it takes care of all the hardware differences. So you don't need to do anything special like marshalling, demarshalling of arguments. You are just simply going to use built-in functionality in Java, which is serialization, to achieve the same thing. Okay? Problem hasn't gone away, but Java already has built-in functionality to deal with it. So we will just leverage that. Okay? So the client will serialize and send all the objects. The server will deserialize and reconstruct not the objects, but the parameters to the method. And the server will deserialize, extract the parameters, and invoke the method. Is that clear? Okay. All right. Okay. So then there is this other issue of how is the client going to locate the server. you remember, these are processes that are running on two machines. As a programmer, you are not specifying any details of where is the server running and so on. And last time I mentioned that the way you deal with it in the RPC world is the server process will register itself with a naming service or a directory service. The client has to talk to the naming service to figure out what port number the server is running on and so on. Okay? Similar ideas are true here. Okay? There are two types of binding. Binding essentially means how do I locate where the server is running and where the object is residing. Okay? One is called implicit binding, where you simply call an object and a method on that object, and then the runtime system will say this is the first time you are making a method call on this object. So it will try to figure out where the object resides in the network, what process, what machine is it running. Okay? That's called implicit. Okay? In explicit binding, you are going to essentially call the bind function, which is going to do that lookup for you. Okay? So you say, I'm going to call a remote method. Okay? The process switch needs to figure out where is this method resident. So we'll call the bind object with the object reference, and it will try to figure out. And then you're going to get the reference to that object, and then you call the method of the object. Okay? That's called explicit binding, where you have to call the bind function to figure out where the server is running. So different RMI and RPC systems will use different techniques, but by and large, it will either be implicit or explicit, where you have to call the bind function to locate the server. Okay? In either of these two cases, this is happening on the client side. The server still has to register itself with a naming service. That part has not gone away. Okay? I'm going to show you some code that shows you how all of this works in Java. Is this clear? Any questions here? Okay. So let me talk about parameter passing before we actually look at some code. Last time when I was talking about RPCs, I said in the RPC world, you cannot pass pointers as arguments. All parameters have to be passed by value. Okay? You cannot pass by reference. The reason is if you dereference a pointer on the other machine, it is going to point a memory address on that machine, not on the sending machine. So that's a meaningless dereference. Okay? So you don't actually pass pointers. Okay? By and large, that concept is true in the Java world, except for one difference, which is if you're passing an object as an argument to a method, which you can. You don't have to just pass simple things like integers. You're passing an entire object. Okay? You can pass a reference to an object that supports RMI calls. Okay? If it's a standard Java object, okay, you will pass it by value. Okay? Which means you'll make a copy of that object and send it with the call, and it will be basically passed by value. But if it is an object that supports remote methods, okay, you can pass that object by reference. You do not have to pass it by value. Okay? If you think about why this is the case, it should be clear why this is even allowed. Anybody want to take a guess why an object that supports RMI calls, not a standard object in Java that's just supporting local methods, but if you write a type of a class where you have some methods that are RMI methods, that object, if you pass as an argument, it will go as pass by reference, not pass by value. Yes. Yes. The reason you don't have to pass it by value is if you invoke a method on that object, you have to have all the functionality to go find out where it is and send the method, send the RMI call to it anyway, right? So you already have a way to dereference the object. I'm putting dereference in quotes here, right? To dereference the object, because that's how an RMI method is going to be invoked on it. Okay? So you can use all of that functionality to simply send that what we call a remote object by reference, because the other end can use the same technique to figure out where the object resides on the network and call a method on it. Right? So essentially, it's a little less restrictive than RPCs. Any standard data structure still pass by value, no passing pointers. Okay? Local objects pass by value. Okay? Any object that supports RMI calls, if you pass that as an argument or method, that will go pass by reference. Okay? So that's what is shown in this picture. May look a little complicated, but it's actually not. Okay? There are three machines, A, B, and C. Okay? There are two types of objects. It's a local object, this standard Java class, okay, that you instantiate. Only local procedures. Okay? Here, So that we'll call object O1. Here's another object O2 that supports some RMI calls, and it's accepting calls over a network. Okay, so these are the two types of objects here. So now you're essentially calling and making an RMI call to some other object on this machine here. So if you pass O1 and O2 as two arguments to a method, okay, O1 is going to go by value, so you will essentially take this entire memory, send it over here, so you make a copy here. So that's passed by value. But that method that actually also took O2 as an argument, that will go as reference because you already know how to access O2 or a network. So you'll just send that, and this process here can also call that method on that object. Is that clear? Okay. There's a small relaxation of what happens in the Java world. So essentially, what is a remote object, or what is the object that supports RMI? If you see the Java code, you will see that if you want to include RMI methods in an object, you are going to essentially have this term before the class. We'll call it a unicast remote object. Okay? That essentially means that this object has RMI calls. Any object that has that, when you write code, you can pass by reference. Okay. All right. Okay. So now, if there are no questions, let me show you some snippet code that tries to explain some of these details. And this is the code also that we will give you as part of your lablet. So you can actually try it on your machine and see how two processes communicate with one another and so on. Okay, so let's start. So we'll do Java, C, Python, and gRPC. 4 systems that all support either RPCs or RMIs in some shape or form. Okay, start with Java. Okay, so I already mentioned the client and the server. There's one other thing I wanted to mention is that you have something called the RMI registry. Okay, so this is the naming service in Java. This is where the server will register itself and all the RMI methods it exposes. So the client can then look that up, figure out where is the server process running. Okay, so you will use not only the client and the server program, but you will use the RMI registry. Okay, so here is some snippet of code. Okay, so there are 3 snippets here. This is the interface of your program. Okay, that's the client part. Okay, just a snippet. This is the server part. So let's start with the server part. So the server is essentially, you will see that it's calling a unicast remote object. So it's constructing an object that essentially has some remote methods. Okay, and then that object essentially implements a say hello method. So you call the say hello method, it sends a hello message back. Okay, I don't think all of that code is shown here, but what is shown is you bind. You basically get the registry and you register the object with the registry. Okay, the code for that object is actually not shown here, but you'll see that it's declared in the interface. So you will see that now you have a hello class that essentially has a say hello method. Okay, and so that's a remote class, which means that you can call that method remotely over a network. Okay, here's the client code. Okay, the client code is first going to go find the registry, and it will say, is there a hello method registered with the registry? Your hello object registered with the registry. And assuming you get that, you get a stub. And then you basically say stub.sayHello. That's your RMI call. Okay, so the code for the say hello is actually in this process. Okay, so the stub code will then send a method. So you will see that the code does not have any networking in it, even though this say hello method is actually going to trigger a network message that's going to be sent to the server to execute the say hello method and get back a response. Is that clear? Okay. So that's the Java example. Any questions before we move on to some other system? Yes.
The lookup part.
Can you skip the lookup part? So question is, can you skip the lookup call? So if you skip the lookup call in Java, it will not work because Java uses explicit binding. So you have to find the object and the method, okay, before you do this. Yes. Okay. The question is this synchronous? Is there a different interface for doing asynchronous? In the Java world, RMIs are all synchronous. Yes, there are other systems that I'll show you that can do asynchronous. And you can use those libraries in Java, but the standard Java RMI is synchronous. Any other questions? All right, so that's Java. There's one more thing I should mention because you will be using this in your lab, which is synchronization. Okay, so why is synchronization important here? So think of the server process essentially is exposing RMI methods. Okay, multiple clients can make RMI requests of that server. Okay, so the server can be threaded. It can process concurrent requests at the same time. Okay, so essentially you will think of this, there are multiple threads that are executing methods on that server or that object that's residing at the server. Okay, because you have concurrency at the server. Server is not doing sequential processing of requests. Next time you will see almost all servers we will encounter in this course will be at least multi-threaded. Right? They're multi-threaded. That means multiple RMI methods can come to the server concurrently. Okay? If you do that and you start modifying any state at the server, you should know that you have to use locking. That's how threads work. The threads need synchronization. Okay? You can't simply let the code execute and then it will modify some private variable and then the variable gets corrupted because you didn't use locks. Okay? So whenever you use threads, you have to use locking. Okay? In the Java world, locking is also straightforward because you have this keyword called synchronized. If you stick that word synchronized in front of any method you write in an object, that method automatically gets a lock, which means that only one thread can execute that method on that object at any given time. If there are multiple invocations of that method at the same time, the locking will take care of ensuring that only one thread is executing in that method. Okay? Different threads can execute different methods of that object, but anything that's synchronized, only one thread can execute it. So the locking is kind of built in into the Java code, so which you can use to implement synchronization when you write concurrent servers. Okay, for RMI methods and so on. So that's how you will do synchronization. Now, if you use something else like Python, you would actually have to use locks and so on explicitly. Okay? In Java world, it's a little simpler for you. But then there is also this question of if two clients are making requests on the server concurrently, only one of on the same object and the same method, only one of them can proceed. The other one will block because the lock will be held by only one thread at a time. Okay? There's a question of, in this case, where should that RMI call block? Okay? Because you have two answers. One is it's blocked at the client. You have not even sent the RMI call until you have the lock. Okay? The other is you send the RMI call. Two RMI calls came into the server. Okay? They are invoking the same method. One of them grabs the lock, it succeeds, and the other one is blocked at the server. Right? So you can either block at the client or block at the server. So these are the two options. Now, there are some issues when you write locks across distributed applications. The specific issue that you have to deal with here is, what if there's a crash of one of these two processes? Okay? So let's say client one grabs the lock on an RMI object and it proceeds. Okay? While that RMI call is executing, the client crashes. Okay? But it's still holding the lock when it crashed. So now, since it never released the lock, no other clients can grab that lock. So you will have a deadlock at the server. Okay? So you have to deal with these kinds of issues when we talk about locking across processes. We will see in a few classes how to implement a distributed lock. A distributed lock is a lock that is shared by multiple processes and has to deal with these types of issues. Okay? By default, you're not getting when you write that synchronized thing, you're not getting any distributed lock. Okay? In fact, the synchronized keyword is going to block at the server. All calls come at the server and they block. But you can also, in the proxy code, do synchronization at the client end as well. That's an option as well. That depends on some implementation. So these are issues that you have to think about when you write distributed application. Okay? But we'll start with simpler stuff first, and then we'll get into more complicated issues of distributed synchronization and so on. Is that clear? Okay. Okay, so now we will switch gears and look at how do you do RPCs in the C and the C++ world. This is only going to be relevant if you write any C or C++ code. which in this class you will not, because all labs will be either Python or Java, but it's something you should know about, because this is the original RPC system. The RPCs were originally designed in the context of C and C and C++ system, and the tools that were designed at that time are still available for you to write any application. We'll be encountering this later on in the course as well when we talk about distributed file systems which use RPCs, and they specifically use C and C++ RPC. Okay? And the lablet actually has code for whatever I'm showing you here. So you will, even though you will not write any code, you will still compile that code and try it and make sure you understand how it works. Right? So, but this is the general process. It's not very different from the 3 pieces I showed you for the Java snippet. Okay? Those 3 pieces: there's an interface, there's a client, and there was a server. Okay? Same thing here. There's a server. Okay? There's an interface which is called a .x file. Okay? That's the interface, and there is a client. Okay? So you'll write, as a programmer, you will write these 3 pieces. The interface will actually say these are, there's no classes here because this is, let's say, it's C code. So you will just have the RPC methods and their arguments and so on. They are the ones you mentioned there. Okay? With C++ code, maybe you can put some classes there, but otherwise you don't have classes. Okay? Then this .x file is first sent to a tool called RPC gen. Okay? That's your RPC compiler. Okay? So that RPC gen will automatically generate your stub code. Okay? That's the code that generated for you automatically by the compiler, so you don't have to write it. Okay? That's the code that's going to do all of the networking. You'll see there's an XDR thing. That's the one that's going to do all the conversion. So there's a server stub, there's a client stub, there's a header file, there's XDR code. Okay? So what you will then do is you'll take these auto-generated files and you will take these 2 files that you wrote. That's the client code you wrote and the server code, and then you'll actually compile them, okay, using a C or a C++ compiler. Okay? So what you will do is you will take the server file, the server stub, header file, and SDR file, and you will get the server binary. You will compile them all, and then you will do the same thing for the client. You will take the client code you wrote, the client code that was auto-generated, okay, the XDR and the header, and you will generate the client binary. Okay? Then you can run these binaries and they can communicate with one another. Okay? Is this clear? Okay? It's important to understand this process because there will be other RPC systems that use the similar process, even though you are not going, they are not C or C++ based. This notion of writing a interface file, or it's also called sometimes an IDL file, interface definition language file. You have a special tool that's your compiler for that RPC system that will auto-generate some code for you, and then you use that code with the client and the server code to implement your RPC system. That process is common across many different RPC systems. It's not specific to C or C++. Is that clear? Okay, so you can play with this in the lablet, and then you can figure out how the process works. All right. So here are some other details that I was mentioning last time, but we ran out of time, which is in the RPC world, how is the client to locate the server? The concept is very similar to what I was just showing you in the Java world, where there was an RMI registry. That was your naming service that you registered the server, and the client went and asked that naming service, where is the server running, and then you could contact the server. Okay? That concept is true also in the RPC world. The naming service is called, also referred to sometimes as the binder. Okay? Binder, naming service mean the same thing. Okay? Binder is a process that allows you to bind to the server. That's our naming service or the directory service. Okay? That is called the port mapper in the Unix world. Okay? So there's a process called a port mapper. When any Unix machine will start, that process will automatically start, and it will be waiting for registrations. When the server starts up, the first thing it has to do is it has to register with the port mapper. And then the port mapper will track what RPC methods are actually exposed, what is the name of the server process, what port number it's listening on. All of that will be registered in the port mapper. That's why it's called the port mapper. It's taking an RPC call and mapping it to a port where the server is listening. Okay? Then the server, the client process, which is now running on some other machine, okay, if it has to contact a server process on that machine, it has to first talk to the port mapper running on that machine and ask, where is this hello world process or whatever that process is where is it executing? Okay, the port mapper will then do a lookup, and if it finds that there is a service with that name running, it will send back a response with the right port number. Okay, and then the client stub code will connect to that port number on that machine, which is that server. The server is listening and send the RPC request. Is that clear? How all of this works? Okay, that's a good question. So what if there are multiple servers that ask for the same service? Okay. So the thing that you have to do is when the server is registering itself to the port mapper, it either has to pick a unique name for itself, okay, or if there's a name, there are two services that, let's say, both provide, I don't know, hello world service. They are just, so you have to at least pick different version numbers. So you can have a name and you have a version number. Okay, you cannot have two services that are running that are the exact same name, because then when the client is asking the port mapper saying, where is this service running, the port mapper will not know which of the two to return. Okay? So either the name has to be unique, okay, the name of the server. So server can say, my process name is X. You can pick some string and register itself. Or if you are using the same service, you have to have different version number. So you can say, I want to connect to version 2 of the hello world service, and then you'll still be okay. Okay, so you have to ensure that these are unique names. Okay? So what this also means, by the way, is if you have writing some code, let's say for your lab, you registered a server process to the port mapper or some naming service, and for whatever reason you terminated it, okay, and then you start another version of that server, it tries to re-register itself, you might get an error if the previous registration has not been removed. Okay, so when you're debugging your code, if you repeatedly register the same name, you might get an issue. So you have to think about some of these things. You can, of course, restart the naming service and it will start with a clean slate. Okay? But the things to keep in mind, you have to have only one server. You can have many servers running here. Okay? They will all register themselves, but each has to have a unique name for the service and a version number. The methods can be same, okay? Because the way you will say is that I contact the server with this name and then I call some method foo. Okay? Each server can have methods that are identical or have the same name, but the server name has to be different or unique. Is this clear? Any other questions here? Okay, so that is the world of C and C++. Now we'll talk about Python. Okay, how are you going to do this in Python? In Python, we have something called Python remote objects, or Pyro. Okay, that essentially gives you similar functionalities, more like Java, because you have classes and objects that you are going to have. The objects will have some remote methods, and then you are going to invoke them. Okay, this is the same kind of snippet you will see in your lablet, but I don't have the full code, but I'll explain some of this, right? So you have essentially a class here, which is going to be like a hello world. It's a greeting class. Okay, you call it, has one method, get fortune, and it just returns hello. Okay, so it's basically returning a string. Okay. So the way you in Python, what you're going to do is this code, this is the server code. Okay, so you have to essentially make it into a server. So the way you do this is you will make what is called a Pyro daemon. Okay, and then you will register that object, greeting maker object, into that daemon. Okay, so that essentially registered itself with the daemon, and then you are essentially going to call what's called a request loop. That's the server is going to just sit in a loop, wait for RMI or methods to come over the network. Okay, so see that you not written any socket code or anything like that yet. It's just simple. You just wrote some class, you made a daemon, you registered the object, and then you essentially said start the server. So that's just sitting in a loop and it's going to start the server. Okay. Now, there are many ways for the client to contact the server. Okay. The simplest way is if you knew the object that you are registered with the server, you can directly use that string. So you will see that I printed in this snippet code the URI of the object that you registered. So it basically has printed. When you run this, this is what it printed, that long string. Okay. you could literally take that string and you could put it in the client code, okay? And that will directly allow you to access the server because that's the object that the Pyro daemon knows about. Okay? So that's one way you are. So this is your client snippet here. Okay? So you are basically, in this case, you're not using a naming service. You're simply, you printed the object ID. You basically input it to the client code. The client code will basically first talk to Pyro and generate some stuff. That's the proxy. Okay? And then you essentially say, this is the object name dot get fortune. So this is your RMI call that you just made. Okay? But remember, here you did not look up a naming service because you are hard coding effectively the address of the server. Okay? Of course, that's not the right way to do it, but you can do it this way. A better way to do it is you are registered this. Okay? Once you do this, you also register with the naming service. Okay? So you'll add this code back here. So you registered the server with the naming service, and then in the client code, you are essentially going to first look up the naming service rather than hard coding the object name, and then you will get the object reference. Okay, yes. In this case, I think maybe this is just a snippet. I didn't have all of the lines of code. Okay? But we'll give you this code. You'll actually have the Pyro code in the lablet. You can look at all of the client and the server. Any other questions? So this is not exhaustive. So the things here not shown. I'm just showing the skeleton of the client and the server. Any other questions here? Okay. So that's your Pyro code. Okay. So this is how you are going to write this. If you are going to do your labs in Python, okay, and you are going to essentially end up using Pyro, this is the type of code you have to write. You do it in Java, you will use Java RMI. Okay. All right. So the last thing I will mention here is essentially Google RPC, okay, which we will use not in the first lab, but eventually the subsequent lab we are going to use gRPC. Okay. G here stands for Google RPC. This is the RPC system that Google designed. Okay. So it's basically a high-performance modern RPC framework. The reason it is actually used is it is not only hardware independent, which both RMI and RPC systems are, it's also language independent. Okay? What that means is you can now write your server code in one language. Let's say you write it in Java. You can write the client code in some other language, Python, and they can talk over Google RPC. Okay? Everything I showed you previously, the client and the server had to be written in the same language. They didn't have to run on the same type of hardware. You could run the server on Windows and client on Linux and so on, but at least the language was the same. Okay, this also provides you language independence, which allows different clients written in different languages to talk to a server. Okay? So what this means is it has to be more general because you have to allow Python code to talk to Java code. So it basically supports a whole bunch of different things. You can write your code in Python, Java, C++, C#, Go, Swift, Node.js. They all support gRPC. Okay? So regardless of the language you picked, you can write your client in any of these other languages. They interoperate. They just work. Okay? So that is why it is now a more general framework. So you don't actually need to use Java RMI, for example. You can use Google RPC libraries in Java and still write your client and server. It will look a little different from the code I showed you. Okay? Because you will use gRPC interfaces to make that happen, not standard RMI interfaces. Okay? All right. That's one thing. Okay? The other thing that gRPC uses is it uses HTTP as its transport protocol. All of the calls that are going over are essentially going over as HTTP messages. As a programmer, you don't need to worry about it. All that is taken care of for you. Okay? But it's operating at a higher level as opposed to RPCs and RMIs. Those are essentially using low-level socket communication to communicate. They run not directly over TCP/IP. gRPC runs over HTTP, which itself runs over TCP/IP. Right? So messages are going back and forth as HTTP messages, and responses come back as HTTP. Okay? All right. And then the last thing that we should know about gRPC is it basically uses an underlying framework called protobuf, or these are also called protocol buffers. Okay? So gRPC is built on top of protocol buffers, and protocol buffers are essentially a language and a hardware independent data structure that allows you to send data back and forth. Okay? Just as I told you, you have to do serialize, deserialize, and all of this type of stuff. Now you have to make that work across languages. You send a message, send an integer, maybe it's a Java process sent it, a Python process has to reconstruct it. So you have to have a hardware and a language independent way to pass data back and forth. Okay? And that in the gRPC world is called a protocol buffer that allows you to construct these data structures and pass them around without having to worry about what is the hardware, what's the language that's going to interpret it, and so on. So it is essentially, think of it as the XDR type format in the gRPC world that's also language independent. So let me show you an example of protocol buffers, and then we'll show you some quick examples of gRPC. And by the way, this is also part of your lablet, so you can look at some gRPC code and run it and see how it works. Okay? So what is a protocol buffer? These are essentially message-based structure, data structures for communication. Okay? So anytime you want to pass some data around, okay, in the gRPC world, you have to essentially create a protocol buffer with the right format, so that's what you are going to use. You just don't pass an integer. You use a protocol buffer in which you're declared an integer. Okay? That's what you're going to do. So here is an example of platform independent protocol buffer, and marshalling, demarshalling, serialization is built into protocol buffer. It is going to take care of all of that. So suppose a client wants to send to a server a string and 2 integers as arguments. You will construct a protocol buffer saying this is a request. Okay? It has a string. Okay? It has 2 integers, and this is how you are going to declare it. Okay? So then what you will do is you will essentially use that declaration, and you'll use a protocol compiler. In the gRPC world, that's called protoc. Okay? It will essentially construct some classes for you. This is like the stub code, but to send protocols data back and forth. This is not yet stub code to make RPC calls. This is just stub code to send this data back and forth. And then you can essentially use the methods of that class to send that data, to extract the fields at the other end. So you get a protocol buffer, you can reconstruct it and say, give me the page number or give me the query that's in there, that's a string. So you can essentially add and extract data from a protocol buffer. That's basically going to be auto-generated for you. Okay? So that is how you will write protocol buffer. Okay? Now, protocol buffers by themselves have nothing to do with RPCs. They are just a way to pass data back and forth in a language and hardware independent manner. Okay? So they're just allowing you to send data structures and reconstruct them and not have to worry about hardware issues or platform issues or language issues or anything like that. Okay? Now, what Google did is it built its RPC framework on top of protocol buffer, because marshalling, demarshalling of arguments are automatically taken care of for you by protocol buffer. So why not use protocol buffers as a way to send arguments back and forth for a RPC system? So they use this as the building block for writing the RPC system, the gRPC system. Okay? So here's an example of a gRPC snippet code. Okay? So we have our service definition, okay, which says this is a service. It's called a greeting service. It's basically going to expose one method, RPC method, say hello. Okay? It's an RPC method. It takes a hello request argument and returns a hello reply value. Okay? Both hello request and hello reply are essentially protocol buffers in our case, because the argument has to come as a protocol buffer, be language independent. The response has to go as a protocol buffer. Okay? So now you got to declare what is a hello request and what is a hello reply, and that's what is done here, saying the hello request is a string. Right? Hello reply is also a string. Right? I mean, it could be anything, but this is just an example. So these two are essentially our protocol buffer definition. That's the definition of the RPC that you are going to implement using this protocol buffer. Okay? So what Google did is they simply extended that protocol compilers to support RPC definitions in addition to protocol buffer definition. This is what you are going to pass to this protocol buffer, and it will now generate stub code that not only allows you to pass these two protocol things back and forth, but it also allows you to write code where the client and the server can call these methods or respond to these methods. Okay? And then that stub code you can use on the client and the server end to write your actual code. Okay? So first you will write this as your interface definition. What are the data structures you are going to use in your RPC calls? What are the RPC calls you will have? What are their input? What are their output? And so on. And then you compile it. Okay? You'll get your essentially client stub code. Then you will use it at the client to invoke methods on the server. Is that clear? Okay. All right. So now we'll talk a little bit about gRPCs themselves. Unlike, let's say, Java and C, which were using synchronous RPCs, gRPCs are more general. Okay? First, they support both synchronous and asynchronous calls. Whatever I was showing you earlier in the slide, gRPC, you can say this RPC is synchronous, this RPC is synchronous, all supported in gRPCs. Okay? Not only that, it essentially has several other things, which is you can essentially send what is called streaming data from the client to the server. You can essentially send streaming data from the server back to the client in addition to making an RPC call. Okay? So you can say, what is the streaming data? Streaming data essentially says that the data you are sending, okay, is not one data item, but you can continuously send multiple data items to the server. And it can then take all of them and process them as a batch. Okay? So rather than sending one integer as an argument to a RPC call, I send a sequence of integers as separate messages. So I'm streaming some data. I get a batch of data. I process it, and I can send back one value, or I can stream a set of values back. Okay? So it essentially has something called streaming RPC support, which we have not yet seen in any of the things we discussed. But gRPC does support that. Okay? Streaming can go from the client to the server or back, which means that both the arguments that are coming in or the responses that are going back, they can be simple integers or strings, or they can be streaming data where there's a sequence of them coming. Okay? Those are only going to be used for specialized cases. You are not likely to write any code that's going to use streaming. You will just write simple RPCs at best. But you should know that gRPC framework has all of this additional functionality. So asynchronous calls can be made, data can be streamed from the client server or in a bidirectional manner, and so on. Okay? So here's an example of you have an RPC where the replies are streaming. So you make one request, and it keeps sending a set of hello responses, saying hello, hello. It's basically send them as different. You'll see that it says a stream is going back. So you'll get a set of strings back as a reply to your RPC. That's a streaming response. Okay? Or you can get a set of arguments as a stream and send back one response. Okay? You can say, rather than getting a single string, I can get a sequence of strings. When all of those sequences are come in, then you process the RPC and send back a value back. Okay? Or it can be bidirectional streaming, where the input is a stream and the output is also a stream. That's also supported. Okay? These are all generalizations of what we have seen as a simple RPC call. Okay? Of course, that's also supported, but you have all these additional things that you can essentially implement more complex applications. Any questions on this? Okay. So again, we will send you a lablet, hopefully today. Okay. So we'll send that to you. You can play with all of these things just to get some familiarity. Okay. We've given all the code to you. Okay. You don't have to write much other than actually run it and try it out. Okay. So I'm going to pause here and show you. I think I'm done, right? Yeah. So I wanted to show all of you the Docker container, which I hope everybody has implemented by now. Okay. But you are going to use it in the lablet and the lab. Okay. So I want to just show you a few things as to how you are going to use your Docker container to do a lab or a lablet. Okay. So I assume you built it already, right? So whatever you built, you are going to reuse across labs. You don't have to rebuild it every time. Okay? You build it once, okay? And that's the thing you're going to use for all of your labs. Okay? So essentially, when you get a lab or a lablet, it's going to have this run script in it, 677 run Docker. Okay? So that's the one you got to start a container. Okay? You do not need to call Docker. First, you have to start Docker. It needs to be running in the background, right? Once the Docker daemon is running, to create a container, you don't need to call on the terminal a long Docker command. None of that is needed. You're simply going to call. So I'm just going to show you for Docker. So to make sure Docker is running, you just call Docker and do something like PS. Okay. If Docker is not running, it'll say cannot connect to Docker daemon. So then you should at least start one. Okay. But if it is running, you will here right now I don't have any container, so it's just saying there's nothing running here. Okay, no containers are running. Okay. So then if you built your image, you want to start the course Docker, you're going to just call this script, okay, and then say run Docker, and then it should be essentially start Docker. Okay, so now you'll get this thing with say 677 use or something. That means you started it, and now that's a prompt inside the container. Okay, so this essentially you have started the container, and the way we have set it up for you is that when that container starts up, all the code for the repository for your lab or the lablet is automatically available inside the container. Okay? So you will see here, so essentially there's a lab0 directory. It should have the same files that were outside on my native thing. So you'll see that essentially you have all of the files that were outside, they're also available in. So you can essentially start the code inside the Docker container that's in the lablet, or you can write new code and test it and so on. Okay? Any changes you make inside the lab or the lablet directory will persist because those are files on your native machine. Okay? But if you go to some other part of this container and make some changes and you terminate the container, those files are ephemeral. They'll go away. Okay? So when you make changes, be sure that you are actually inside the lab directory, because that's the same directory that's outside. So any files you create, when you exit the container, they stay there and you will see them outside as well. Okay? That's important. Otherwise, you will write some code in some other directory and you kill the container, the changes are gone. Right? So don't make that mistake. Is that clear what I'm saying? Okay. So now the other thing you don't want to do is if you're running a container, you don't want to call that script inside the container. Obviously, you can't start a container inside other container. It will give you an error. Okay. So whenever you call the script, it has to be on your native terminal. Okay. If you have some prompt like this and you try to run it, it will give you an error. Okay. Now, the other thing I will show you is if I go here and now do Docker PS, it will show that I actually have a container running. And now you see that the one container is started. Okay. The thing that the Docker PS command is useful because it will tell you the port number where the container is listening. That's what you will need for two containers to talk to one another. If you start the client and the server in two different containers, you need to know port numbers so that they can talk. Docker PS command will tell you that. Okay, that's one thing. Now the container gets its own IP address, which is separate from the IP address of your machine. So each container will get its own IP address because Docker will create a network. And the way you are going to figure that out is this is a Linux command. If you call IP space address, okay, that will print all the interfaces on the machine. But just to make it simple, I'm only going to extract the inet addresses. So you will see that it returns you some interfaces. Ignore the first two. You'll see something that's 172.17.0. That's the IP address of the container we just started. Okay? You will need that if you need to know what is the server IP address, because if you start the server on one container, that's the IP address of the server. The Docker PS will tell you the port number that's listening on and so on. Okay? So these are things you should know. I'm just showing you so that your life is a little simplified. Okay? Okay. So suppose that you now have a container already executing. Okay? And then you go back to another terminal, because I just switched from this. This is my running container, switched to a different terminal window. And now I call this script again. Yeah, I call that run script. Okay? So what it does is by default, if you just call that script, it is not going to start a second container. Okay? Because it just checks if there's a container running, it connects to the same container. So if you do this, it will basically print some command saying there's a container already running, and it will just connect to that. So now I got a different prompt, and this terminal prompt and the previous one, they are essentially in the same container. They are not two different containers. Okay? And you will say that it will say, if you don't want to do this, go kill it or do something else. Okay? And you can verify this with the docker ps command, right? So it will show you that there is only one running still, even though you called that run script twice. Okay? But there will be instances where you need two or more containers. You want to run the client in one, the server in the other. Okay? So you essentially what you'll have to do is, let me just kill that one. So you have to call the run script with the -f argument, which says start a fresh container, even if one is already running. Okay? So if you do this, it will give you again a prompt, but this is now a different container, not the one that we have. And you can actually go back here, and if you do docker ps, it will show you now there are two of them running. Okay? You will see that they're also listening on two different ports. So each got its own port and so on. Right? And you can create multiple like this, but you have to give the -f command for it to create one. So if, otherwise you will not be able to do it. Okay? So the script already takes care of lots of details for you. Okay? You don't need to start by hand. Just use the script with the right arguments. It will take care of things for you. It will take your GitHub keys that you created. It will automatically mount them so they're inside the container. So you can do git check-in, check-out from inside as well if you want to directly check in code, etc. Okay, is that clear? Okay, so the last thing I want to show is this. If you essentially have, let's say, Visual Studio Code, and you implement, so this is the editor you can use to write your code. But the interesting thing you can do with this is it can directly attach to the container, so you can modify files inside the container from your native machine. Right? So all you have to do is you have this left thing here, right? That leftmost corner bottom. So you click on that, it will open this and say you say connect attach to running container. Okay? So to show that, it will show you the two containers because I have two running now. Okay, I can pick one, and if I attach to it, it will basically start this. It will attach to the container, and then all the files inside the container are now available here. Right, so you'll see that I have lab 0, and all the files are here. Right. So you can simply just use Visual Studio Code attached to the container, modify the files. You can check in and check out directly from here. Don't have to use the terminal. You can just use an editor that has container support to directly edit code inside containers and run them. You can start terminals from here as well. Okay? So Visual Studio Code is another good tool. It allows you to do this type of remote development. Okay? Technically, it can connect to a container anywhere. It doesn't have to be running on your machine. It can connect to a container in the cloud, and you can do remote development this way. Okay? So just wanted to show a few of these things so it's clear how we are expecting you to actually write code and so on. The good thing is, regardless of what machine you have, okay, you are going to work inside the container, and everyone has the same environment. So it won't be a case where it's not working on my machine because some environment variables are different or I install things differently. It should work the same for everyone because the same development. So you're going to use the same Linux containers, Linux for everyone, right? Whether you are using Windows, Mac, or Linux, the development environment is Linux. Okay? Is the same Ubuntu environment for everyone, same libraries. So it should work the same way. Okay? Hopefully, it will cause less problems. But otherwise, we spend half the time trying to figure out what your setup is before we can help you with anything at all. Okay? At least that problem is gone. We know what your setup is now. Is that clear? How we are expecting to use all of this? Okay. So, if there are any questions, I can answer them. If not, we'll end it here. There was some sign-up sheet that was going around. If you haven't put your name, just check your name against it so we know now that add drop is kind of done, right? I want to know who is actually in the class and who's coming and what. Okay. So we'll stop it here and we'll continue next time.